So, in the last lecture we were discussing the mechanisms which cause a change in the Atlantic meridional ocean circulation. Okay. And we looked at the results from a coupled model. Okay. Now, coupled models are fairly complicated, they are very rigorous models. So, normally people compare the coupled model with what is called the box model. Okay. In a box model you have just 3 boxes, and the 3 boxes are here the polar region is one box, and then you have the troposphere south and the deep troposphere. Okay. And so, this is the deep tropical box that is close to the equator, and this is the surface, because the difference between surface and deep is important. Okay. Then you have a polar box where all the action takes place. Now, this simulation should be compared with this simulation, which is more complicated. This involves many layers in the atmosphere and ocean. Now, the reason I am showing the box model is to point out that the box model more or less reproduces the changes simulated by the coupled GCM. Okay. So, in the coupled GCM we have many more layers, many more regions, but we average for the same region as the box model, and we find that box model does quite well, not perfectly, quite well compared to the coupled GCM. Okay. So, this is to illustrate that once we have got a coupled model which correctly simulates the observed changes in the circulation, it still needs an even simpler model to understand how these changes occurred. Okay. So, we have the observation, we have a complex coupled model and a simple model which to go together. Okay. Now, subsequent to as this work was going on with a coupled model, Stefan Rahmstorf did a lot of work to understand the Atlantic meridional ocean circulation, and for that a group of scientists ran about 12 to 13 models, okay, of various complexities. Somewhere at the bottom here are full 3-dimensional models here, and there is a model here which is just 3 basins, and then there is zonally average model. You do not worry about zonal variation. So, the idea is to run many models with various levels of complexity and find out how the North Atlantic deep water, which is created by this Atlantic meridional ocean circulation, when it goes down near Greenland, it causes formation of deep water. Okay. So, it is a measure of the AMOC. So, you can see the different model produce and as you introduce the freshwater flux near Greenland in millions of meter cube per second, the deep water formation starts slowing down. So, the whole purpose of this exercise is to see how the introduction of fresh water slows down the circulation. Okay. And you can see that there are here 5 models here and about 11 models total. All the models show a slowing down of the circulation, but they slow at different rates. Okay. Some model like the here I believe the EC built shows a rapid decline, while the University of Victoria model shows a slow decline. Okay. So, this is a big challenge for us now, because we know that as the Greenland ice melts, more and more fresh water is being deposited in the North Atlantic, and it is going to slow down, but the models do not agree on when they will slow down. As the fresh water goes on increasing, when they will slow down, that is one part. Second part is very important, we will discuss that in detail. When does it shut down? Shut down means no flow. Okay. Starting with around 20-25 meter cube per second, all the models show that at some point they will completely shut down. Okay. And if that shutdown occurs, it will have serious consequences to the Earth's climate. This is one of the concerns which are discussed at great depth before the Paris Agreement among nations, because these model simulations showed that due to the increase in carbon dioxide, if the temperature, global mean temperature went above 2 degrees centigrade, then there is a chance that this Atlantic meridional old circulation will come to a stop. And if that happens, there will be very serious consequences to the global climate. So, these simulations tell you that yes, it is slowing down, but they show that the shutdown occurs at different times. For example, this model says shutdown occurs when you add a fresh water equivalent to 0.2 Sverdrups, while the model in blue says it occurs around 0.35, while the green says it will occur around 0.45. Now, this is a very big difference, because these changes occurring at different freshwater input implies a difference in time. So, between here and here there may be a difference of 100 years. So, this is an issue. There are some people now saying that due to global warming, the Atlantic meridional ocean circulation will stop in another 20 years. Others are saying it will stop in 50 years, and other simulations showing 100 years. Now, this is of course a cause of worry. If 20 years is a very short time, if AMOs is going to shut down 20 years, we will have serious consequences to global climate. But if it is going to occur after 100 years, we still have time, we can do some quick changes to our emission of fossil fuels, and so slow down the time it takes for the AMOs to shut down. So, these models show there is a lot of variation. Of course, these models were done about 20 years ago, but more recent models show better agreement, but still there are differences. Now, one of the models that was discussed by Stefan Rahmstorf was known as the Potsdam model, and it has a statistical dynamical atmospheric model, not the full atmospheric model, but a statistical dynamical model. It has a land surface model and energy balance model and a dust model. See, dust model is important because during the last ice age, when the Earth's temperature was about 5 to 6 degrees lower, there was a lot less rainfall over the globe, and hence lot more dust in the atmosphere. There were many more deserts, and so the dust storms increased. And dust, of course, reduces the solar radiation entering the Earth's surface and also absorbs solar radiation and warms the atmosphere. So, dust plays an important role in Earth's climate, and it has been included. They also had an ice sheet model and ocean model. So, only simplicity that Potsdam introduced is regarding the atmospheric model, because their main focus was on the ocean model. Now, some of these models show details about both the variation with latitude as well as the vertical structure here. The longitude is shown here around Greenland, and of course the latitude and also the height. So, this is a 3-dimensional picture you are getting, and it is showing that when the Heinrich event occurred, that is a lot of icebergs fell into the from North America and Greenland, iceberg discharge. So, it caused a lot of cooling in the North Atlantic, and on the other hand around the equator the temperature increased because the Atlantic Median ocean circulation had slowed down. Okay. So, the three-dimensional picture gives an idea as to what happened during the event when icebergs fell into the ocean. Okay. Now, this is a simpler thing to look at, the vertical structure only, and you see that you only compare these two. So, when the icebergs fell into the ocean, you can see that the temperatures, this is the circulation pattern they are showing here in Sverdrups, that is millimeter cube per second. You can see that during the Heinrich radial event, when a lot of icebergs fell into the Atlantic Ocean, the circulation was weaker. Okay. On the other hand, when the warm event occurred, the circulation started increasing. Okay. And finally, during the boiling Alert phase called the interstadial, that is a warm phase during the glacial phase, the circulation went up further. So, what it shows is that when icebergs fell in the Greenland region, the circulation became weak, then it slowly recovered and it became stronger. So, the AMOC strengthened here was weak here. Okay. So, other thing which happened, which also is well known, is that when the water came out of the melting of the ice both over land in North America as well as Greenland, it also brought a lot of debris. This is called the ice rafted debris, IRD, and this debris falls into the deep ocean, and once you go and drill into the deep ocean, you will see layers of this debris at certain times, showing when the Heinrich event occurred. So, Heinrich event is very well documented in the marine core taken from the bottom of the ocean. So, what it shows is that during the last 800,000 years, the Atlantic meridional ocean circulation fluctuated a lot, and these are called the DO variability, that is the let me just mention clearly here. These are the Dansgaard-Oeschger oscillations. Okay. These oscillations occurred every few thousand years during the last 800,000 years. You keep seeing these oscillations in the marine core data, in the ice core data in the northern hemisphere. You see these oscillations which are well documented and studied in great detail, because we want to understand what causes oscillations and how such oscillation may occur in the future. Okay. So, both the paleoproxy records and numerical simulation provide strong evidence that the Dansgaard-Oeschger variability was associated with changes in the strength of the AMOC. So, that was a major discovery which was very important, that the oscillation we saw in the ice core data and the marine core data are linked to the changes in the ocean circulation, that is a Atlantic meridional outer circulation. Okay. Of course, no climate model has fully replicated all observed climatic and biochemical changes, but they are pretty good at demonstrating the occurrence of this oscillation, but details we still do not get all the details correct. Okay. So, let me again show you through a cartoon how this ice rafted debris came. They came because the huge Laurentide ice sheet, which occupied almost most of Canada and North America, when it started melting and water came out from these melts, they brought along with them, because glaciers carry rocks and stone along with them. Okay. And those stones and rocks fell into the ocean and ultimately dropped into the bottom of the ocean, and today we can recover it by drilling ocean cores. So, ocean cores are a very important proxy indicator for the occurrence of ice rafted debris. So, whenever ice rafted debris is seen, you know that during that period the Laurentide ice sheet was melting and depositing icebergs which contain these rocks and debris. Okay. So, this is a very important data which is obtained from the Atlantic Ocean deep ocean cores. Okay. Now, for you to appreciate how the ocean circulation is sensitive to what is happening at the surface, here is a counter example from the tropics, where they show that during weak monsoon years, Nile river does not flow into the does not provide some water to the Mediterranean Ocean. At that time, there is normal deep ocean circulation, because when ocean water evaporates to the top, it becomes denser and it falls, and this occurs. But during strong monsoon years, when a lot of Nile river water flows on top of the ocean, it provides a lid which prevents the ocean from losing water by evaporation. So, the salinity does not change and there is no circulation. Okay. And deep ocean does not get oxygen. The oxygen comes to the ocean only from circulation of oxygen containing water at the surface to the deep ocean. That is completely gone, and so we can, by looking at the ocean cores, look at when the circulation was active and when it was not active. So, you must remember that surface of the ocean, whether it is getting ocean discharge or ice discharge, controls the deep ocean circulation. Now, I want to show another simulation here and data. The data is in black based on oxygen isotope 18 data in ice in Greenland, and the orange line is the simulation for the last million years in a model which did not include meltwater forcing. You see, the meltwater forcing is not there. It currently reproduces the gradual decline in the annual mean temperature of the earth over 1 billion years, but does not reproduce these oscillations. So, what it shows clearly is that these oscillations, whose time scale is 1000 to 5000 years, are not caused if you do not introduce the meltwater forcing. So, this shows beyond reasonable doubt that the Heinrich event and the Bowling-Elleroyd phase were a response to meltwater fluxes. Okay. So, this is the advantage of using models. You can shut off the meltwater forcing, add the meltwater forcing, and see what changes occur to the global mean temperature. Now comes the important understanding of why the Atlantic meridional ocean circulation shut down. Okay. It shut down because AMOC is sensitive to freshwater forcing, which also depends on CO2, and if the freshwater forcing is very large, the circulation suddenly stops. Okay. So, this is the stable phase of the circulation, which is slowly declining in response to either CO2 increase or freshwater forcing. At some point it suddenly stops because this part of the curve is not stable. Okay. So, this is the stable part of the circulation of AMOC, this is the unstable part. So, as soon as it goes to the point B, it just shuts down suddenly. Okay. So, our interest is knowing when will the point B occur, because right now the Atlantic meridional ocean circulation is slowly declining, but we do not know whether it is due to the melting of Greenland and some other for example sea ice in the Arctic, or is it due to natural variability. We saw that the Atlantic meridional circulation has a natural variability of Poiet and Swerdrups due to year-to-year variation in ocean temperature and circulation. But we are concerned about the long term, because we know that sometimes this circulation stops. So, this is the thing which you want to understand and which we will now discuss in some detail. Okay. To understand this, the famous oceanographer Henry Stommel proposed a model which is very simple. So, I am going to discuss that model because for me it is very important that you just do not believe the simulation of climate model. You must understand why that circulation stopped through a simple model which you can run in your own computer or even calculator. So, for that Henry Stommel proposed a simple model, and I have taken this next couple of slides from the book Global Warming Science by Eli Zipperman, which I mentioned earlier, and this model consists of just two boxes, a warm box and a cold box. Okay. The cold box represents the polar region and the warm box represents the low latitudes. Okay. And the idea is that due to the Atlantic meridional ocean circulation, some flow comes in here. So, flow with a different temperature, salinity and density comes into this box and alters the temperature, salinity and density of this box. Okay. And due to mass conservation, a similar amount of mass has to go back to the tropics. Okay. In addition, there is of course freshwater addition at the top, either a low latitude or high latitude. Okay. So, in this two box model, we look at the change in salinity of the box 1 here due to Atlantic meridional ocean circulation here coming in here, and this shows the difference salinity between the two boxes. Okay, into the flow into the box. Okay. So, if you are getting flow from this box and S2 is not equal to S1, then this difference will cause a change in S1. Okay. Plus of course, the role of the freshwater flux, which can reduce salinity. Now, in box 2 we have the reverse. Whatever happens here happens in reverse here, this changes, and the freshwater flux also has to change. Okay. Now, what controls Q, the flow rate between the warm box and the cold box? So, Henry Stommel assumed a simple model that the flow must be proportional to the difference in density between the two boxes. Okay. The density difference multiplied by some empirical constant controls the flow rate, and the density difference is due to either change in temperature or salinity. Okay. Both play a role. Okay. And so, alpha is the rate of change of density with temperature, beta is the rate of change of density with salinity. Okay. So, density of water can change both due to temperature and salinity. So, we accounted for both these factors. Now, this is a repetition of that fact, and we also calculate the salinity change in the box due to evaporation from the surface of the ocean to the atmosphere. A is the area of the ocean. Okay. So, one point is that the salinity in the ocean varies between around 34 to 36 parts per thousand. Okay. And we are going to assume that all the change in the circulation occurs only due to salinity. This is a simplification. In reality, both the temperature and salinity change contribute to the change in density and the flow rate, but we will only focus on the change due to salinity. Okay. If you take those two equations and write down T1 minus T2 as delta T and S1 minus S2 as delta S, then you get the two equations simplified now for the two boxes. Okay. And this is the freshwater forcing. Okay. And for convenience, we define x as alpha delta T, y is delta delta S, and you can write those equations for y less than x and y greater than x, and you get one solution for y less than x and two solutions for y greater than x. Okay. So, there are three solutions, okay, which we have to be concerned about, because this problem has a multiple solution. Just remind you, this is an attempt to understand this problem. It has multiple states, and we are trying to understand those two states. Now, in the steady state, when change in salinity difference with temperature is 0, that is what we are looking for as solution. And you see that there are three solutions here, where d delta dt is 0 steady state, two are shown in solid and one shown in open. Okay. These two are stable, this is unstable. Okay. So, why do I say that? This is similar to what we discussed when we discussed the stability of the global mean temperature. There they showed that there are three solutions there also, and two of the solutions were stable and unstable. The same argument here, because we are at this point, the red point, which is stable, and slightly change the salinity, you will find there will be a reaction which forces the salinity to again to change, such that it goes back to this spot. Same thing here. If you slightly perturb this green point, the salinity will slightly change, which will make the system to change the temperature and bring it back. Okay. So, one can show that these two are stable and this is unstable, and so this is a model that Strommel proposed more than 63 years ago. But there are some people not happy with the model. They like to introduce a tropical box. Here we have only two boxes, the low latitude, high latitude. Now, there are people who have introduced slightly more complex picture with high resolution southern latitude, high resolution northern latitude, and tropical region. So, this slight extension of this model, but the spirit is still same. You will still get similar solutions, but it is a little more complicated. Now, we just explained how the circular changes occurred in the period from 20,000 years ago to 40,000 years ago due to changes in Atlantic meridional ocean circulation. Now, to test this model, people also looked at the last interglacial. Remember, we are in interglacial right now. We came out of the ice age, we are in interglacial, but we should look at also the last interglacial, which occurred around 120,000 years ago, and then also the ocean came out of the Earth's system came out of a cold climate to a warm climate, but there are differences between these two. So, people are trying to simulate these two simulations to get an idea of what controls the changes here and here. Okay. So, this I will discuss in the next class, where I will look at a paper where they have compared the AMOC changes in two different periods. One is the present simulation between 20,000 to 40,000. The other one is 100,000 years ago. Okay. So, by comparing those two, we will be better able to understand how these changes occurred, because we have one more data set going back to 120,000 years ago. Okay. We will continue the discussion in the next class.